Okay, so welcome to our second SPCL Bcast this year. We're back online with Jeff Hammond from Intel HPC. I'm very glad to have him, and let Nikolai introduce him.
Okay, thank you for coming, everyone. So Jeff is a principal engineer at Intel, where he works on all sorts of high-performance computing topics. Previously, he was at Argonne at the Leadership Computing Facility, where he worked on BlueGene and MPI. His PhD is in physical chemistry from the University of Chicago, where he did a lot of work on NW-Chem. And now we'll let Jeff talk about the excellent parallel research kernels. Thank you.
Hey, thank you. So I'll be talking about the parallel research kernels, which is something I've been working on since I joined Intel. It's definitely not my project, but I'll explain that in just a second. But it's something I think is quite cool. I've worked on it now for a while on a bunch of different projects. And what this talk is really going to be about is explaining why this thing exists and what we use it for. I'm going to have some results, but the point of the talk is not the results. The results are just to show you that the tool, that it's the PRK, as I'll call it, is a tool that can tell you things about computers and software that you might be interested in studying. And I want to make it clear, I'm wearing my academic hat today. This is not in any way related to Intel products, and actually I'll talk about a variety of hardware, not really focused on anything, Intel HPC hardware, just because that then it gets easier to confuse me with sales and marketing. So I'll just show you some data. And yeah, so the research artifact here isn't the data, it's the code, and you'll see where to find that in just a second. So very much please check it out later. You'll learn a lot more from the code than you will from the talk. Okay, so this is a big project. So Tim Mattson created this a long time ago to study a wide variety of things related basically to microprocessors. This is, before even multi-core, I think is this project has existed. Tim was interested in studying branch predictors and TLBs and memory controllers and things like that. Rob van der Wingard is a former colleague of ours now at NVIDIA, who did a whole bunch of the work to build a foundation that was used to study parallel programming models. And then we had a group of people at Intel and the University of Washington who added some stuff, and I'll talk about that study real quick. It's published in ISC in the past if you want to know all the details. And then I've gotten a whole bunch of help over the years from a lot of different people, telling me what was wrong with the implementations that I wrote. I think last time we counted, there was 56 different programming models and languages in the PRK. At least a few dozen of those were my creation, and I'm not capable of understanding all of them perfectly. So I just phoned a friend a whole bunch of times, especially on things that were hard for me, like Parallel STL and TBB and Fortran 2008. And it's been neat too. There are some folks, I think including Torsten, has written a paper with this stuff. So other people have used this. This is very much designed to be a community project that anybody can use and contribute to, whether or not we're involved. So that's the main GitHub repo. If you want to check it out, if you're the type of person who wants to multitask and read code, feel free to do that now, and I'll try to provide some pointers to where you might want to look at various stages. So the primary usage that the PRK has now is programming model evaluation. It turns out there's a lot better ways to evaluate branch predictors and TLBs than what we've written. But what we've created is something that makes it pretty nice to evaluate different software models, and more importantly, to do it quickly. So I think many people in the call are familiar with things like the NAS parallel benchmarks, mini applications, Lulesh, MiniMD, etc., and the HPC challenge codes. And those are all really good. Many of them are, in fact, complicated, even though they're supposed to be mini or proxy things. It might take a couple months to do a really good job porting Lulesh to a new programming language. Maybe changing to a new C++ model would be easier. But you still have to know some stuff about what's going on to do the port. If you're a pure computer scientist who doesn't know anything about PDEs or physics, it might be hard to understand. And so one of the things that we're trying to do in the PRKs is sort of be the mini or proxy version of those things. And you'll see in what we've used, or what the different kernels are, that the NAS parallel benchmarks and HPC challenge are actually the inspiration for some of them. For example, there's the Fourier transform, the NAS FT benchmark, which is itself relatively simple, but it turns out if you really want to do performance analysis on that code, it boils down to doing a pencil style matrix transpose, 1D decomposition, and doing it all on the data, because that's really where that that NAS kernel is going to slow down and tax the hardware. So what we did is, or what Rob and Tim did, is they pulled that out and just measure that. So we can learn a lot even from that, and you'll see some interesting data. And you have to ask yourself what you're even trying to measure in the first place. So sometimes you want to measure productivity and elegance. Obviously, the HPC challenge has had, at least in the past, a qualitatively judged elegance competition, which I think is extremely hard. So, we're not publishing any metrics on this. You can decide what productivity and elegance are. I will say, having done some of the ports, I can say my own experience was, here are things that are hard for me or easy for me, but some of that's because, I learned Fortran first. And so maybe I'm a little bit demented. The other thing you can measure along the way is implementation quality. So, because I work for a vendor that has a HPC optimizing compiler, we like to calibrate that. And so I can figure out that GCC, ICC, Clang, et cetera, do a better or worse job, or maybe there's bugs in compilers. Turns out I found a bug in either a performance or a correctness bug in every compiler I have ever used with the PRKs. Many OpenMP 4.5 compilers have issues in them, and some of them are performance. So GCC and Clang actually tend to be correct most of the time, but the performance can often be junk. ICC does a really good job with performance, but in some cases has been a little bit too aggressive and optimized out inner loops or other things. So that bug is 3 years old and got fixed a long time ago. So don't worry about that one. But you can also look at measuring, things like asynchrony. So if you compare like MPI send receive with UPC, obviously you're measuring a different thing, because one of those models separates data. So UPC memput followed by a flag update is you could completely separate data movement and synchronization. MPI send receive couple them. Of course, MPI also has RMA, and those are decoupled. So you can use these to measure sort of the semantic differences in models, and I think that's a really important factor as people benchmark PGAS versus send receive type models, where they often say, "Oh, our model is better," and it's really just that our model has less synchronization on the critical path. Not the, or maybe our implementation has more RDMA optimizations than somebody else's, but it's important to separate out those factors, and the PRK does allow you to do that in many cases. And then, there's a lot of really hard questions that we can't answer very effectively. Talking about things like whether you use atomics or coloring, whether you use, one-sided or two-sided. There's some things where you can do an objective job and implement two things side by side. And there's other times that's just a design decision that comes out of the application developer's head. And they say, well, I'm intending to do it this way, and if I design my app around that, that biases the results towards one thing. So this is where the PRKs are nice, in that you can maybe do some of those experiments in a quick and dirty way, and then hopefully inform your application decision, so you don't have to write two versions of the same gigantic HPC code and then before you know the answer. And there has been some work to understand things like load balancing. So that's an example of MPI doesn't do load balancing. You do load balancing with MPI primitives, but models like Charm++ do load balancing for you. So if you write a code that, if you compare MPI and Charm++ for something that has a great deal of load imbalance, you're going to get very different results. And that doesn't mean that MPI is worse, unless you're judging MPI on the fact that it didn't do the load balancing for you. And that also can be really important. And so you can see some of these things. There is a PRK or two that Rob has created both the PIC and then AMR kernel. They're way more complicated than the stuff I tend to work on because they have to be. That's the unfortunate nature of creating load imbalance and doing it in a way that's actually meaningful is hard. So those codes are there. We haven't done as much study with them, but we do understand that this is one of the gaps in the project. We just haven't had time to fill it. So the goals here. We want to be as universal as possible. Clearly, that's not going to happen. There's a strong HPC bias, although some of our kernels, while they come out of HPC, the algorithms will actually show up. For example, our stencil code is designed to look like a stencil that you might see in an HPC code, but the data access pattern is probably identical to a Gaussian blur that you'd see in Photoshop. So maybe it's more universal than just HPC. The other thing that's really important is simplicity. So we want the PRKs to be defined by math and something you can write on a chalkboard, not a piece of code that then gets optimized here and there and everywhere. The reference implementations for a very long time used C89, and that was kind of difficult when we wanted to collaborate with people who had languages that didn't look like C89. And that's one of the reasons for generalizing some of the language work that I have done over the years. We also, now I probably use the Python implementations as the reference, even if, because that's the most readable code you can find in the project, but you can also define them in terms of equations and pictures if it helps. We want everything to be as portable as possible. We have run everything here from Cray systems, Blue Gene when it existed, GPUs. I haven't done anything with any other accelerators lately, but definitely CPUs and GPUs. My rule is if you can't port the PRK to it, it's probably broken and shouldn't be used. But that's not necessarily a hard statement. Extensibility. So we want these, unlike some of the benchmarks that you'll see out there where it's like, okay, this is clearly designed to run at a certain scale. We want to be able to run from every scale, from a Raspberry Pi to an exascale system. I've certainly run this stuff on a Raspberry Pi up in my closet. I've run them on, integrated graphics, discrete graphics, NVIDIA, Intel, IBM, ARM. You'll see A64 data later. So there's a lot. Clearly, we've been pretty successful in terms of the extensibility of these. You'll see the language extensibility later. We also want to be verifiable. So it's pretty important to not measure garbage. And so the PRKs, to the best of our ability, will, if you do a new port to some new programming model and you cheat or you forget a barrier here or there, hopefully we'll catch you. It's not perfect. Sometimes the hardware is forgiving, but we try very hard to make sure that you only get a performance number after you've gotten the right answer. And this is mostly just convenience for computer scientists that you only have to look at 5 lines of code if you need to, and then it will check the results for you. Assuming that you haven't changed things too dramatically to break that code. These are definitely not designed to be used as hardware benchmarks. Part of that is because the lawyers tell us we're not supposed to be creating hardware benchmarks as vendors. But it's also just that these are tools. These have not been created to be an HPL or whatnot. You can measure bandwidth pretty effectively, but definitely don't use anything else besides the bandwidth benchmark without optimizing it, because benchmarking hardware with unoptimized code is pretty silly. So the PRK components, I boldfaced the ones that I'm going to talk about the most. As you can see, they're all very simple. You can understand them from the pictures. So you've got a dense matrix transpose with a 1D decomposition that's designed to match the way an FFT works, not the way a matrix multiply might work. There's a star and a grid-shaped stencil. We just look at star, usually with radius 4. That's obviously low floating point intensity, but it's a great way of taxing synchronization and memory. We know obviously that there are many people in the world who know how to get optimized stencils, but it usually takes a great deal of work and makes it harder to do measurements from one machine to the next, because all the optimizations for stencils with registers and caches tend to make them less portable. So we want to avoid that. You can of course do all that optimization work yourself downstream, and if you think it's useful, you can contribute that back. But the canonical implementation is one that is sort of universally good or bad everywhere. Vector addition, it's basically the stream triad with accumulate. I'll mention some more on that later. And then there's something called, it goes by the name sync P2p. I also call it Wavefront. I'll talk about that at the end. That is one of the more interesting benchmarks. I think it captures a pattern that is a lot harder for many programming models, and we've learned a lot out of it, especially with tasking stuff. And there's other stuff in here. Not all the non-bold-faced ones have been ported nearly as much as the others. Some of them, like the DGEM benchmark, are anybody can write a simple program that calls DGEM. Although we have done some work with multi-GPU DGEM stuff that at least maybe that's code that's convenient for somebody if you want to create a space heater out of your gaming rig. So we have the thing we call NStream, and that really stands for it's not stream, out of respect for McAlpin, who's very clear about what is and is not stream. So I work on stream a lot, and this is different, and it's different in a way that I think is interesting, and others have found this too. So the folks at Bristol have actually looked at what we've done and decided that the thing we're doing that differs from NStream or from McAlpin stream is worth adding to Babel stream. So what we do in that benchmark for correctness verification reasons is that we always accumulate into the output array. And so plus equals. And the reason that matters is that if you are accumulating, you always load the output and then you write it back. And so you always do one load and one store. Whereas in the case of the stream benchmark that does equals and just does assignment, you will either read then write or purely overwrite the output, depending on whether or not your compiler generates a non-temporal streaming store or not. And this, of course, then means that the stream benchmark numbers will be dependent on what your compiler is doing. We also see the same effect in the Fujitsu compiler with A64FX. I don't know why, because I haven't read enough A64FX assembly, whether it's a non-temporal thing or just some other effect. But we think that if you want to measure bandwidth, you should be able to measure bandwidth without worrying about what your compiler is doing. So this is clearly something that makes it easier. I think all the people in the world who do benchmarking for a living with stream do the right thing, and the marketing numbers are what they should be. But it's really easy with the stream benchmark to be, if you're naive, to do something with GCC and get a number that doesn't match up with the DRAM numbers. And so we like to make that sort of idiot proof. The stencil is 2D. So, I've been told that it isn't as bad as I usually say it is, because if you do a massively parallel distributed 3D stencil, you end up with a 2D limit locally. It's also the case that an image convolution sweeps the data in the same manner. We have a transpose with a 1D decomposition, which, in distributed memory generates an all-to-all type pattern with small messages. It also blows out TLBs within a node, and we block it for that reason. So it has a different, sort of a different characteristic at different scales, but still interesting, and you can use different implementations at different scales of memory hierarchy. Finally, the sync P2p or P2p Wavefront benchmark is very different between shared and distributed memory, but it's quite interesting in both. I recall Torsten and some of my Intel colleagues had a paper where they did something with SHMEM, where it's a baton passing synchronization test. In shared memory, you don't have to have that same synchronization, but you have the same data dependence, and that can manifest itself in different ways. And I'll go through that later. So Tim created this thing a long time ago, and Tim and Rob did a lot of the work, so we built on that. The thing we learned when we did the exascale study within Intel Labs when I joined was that the C89 stuff we were doing was good for C89 based models, but not good for other things. So we were looking at Charm++ and Grappa, which are obviously C++, and starting with the C89 reference code and then trying to use C++ is a little weird. Obviously the languages are forward compatible. but that doesn't mean that you end up with pretty code. And the Charm++ people were pretty clear that starting with C89 was the wrong thing to do, but they helped us fix it. And of course, UPC is ever so slightly not C89, because it's based on C99. And then we started talking to Brad Chamberlain, who is really the inspiration for a lot of the stuff that I have done with languages. Brad likes to emphasize that Chapel is multi-resolution, and that you can write Chapel that's tuned and requires more work, or you can write Chapel that is super, super compact and quote unquote pretty. And so I've tried to mimic that analysis by writing different versions of code. Like in Fortran, we can write a version with loops. That's the classic way to write Fortran. Or you can just use the colon operator and intrinsics and write code that looks a lot like MATLAB. MATLAB, you can also write loops if you want, but I don't think any sane person does if they can avoid it. And this allows us to talk about expressiveness and what sort of intrinsics a language might have that would be useful. When I left Intel Labs and moved into the HPC org and started thinking about building exascale systems, it was pretty clear that the future was going to be heterogeneous. And so I really wanted to understand the models, but I wanted to understand them through C++ and Fortran, because that was what it seemed likely that people would be using rather than C89. And the differences mattered because, as I think everybody knows now, within C++, we have a lot of different ways of handling GPUs. Obviously, there's Cocos and Raja, and then there's, Intel's working on SYCL 2020, which is, the deeply C++ compiler people hear about. And then there was multi-GPUs. And so that's been something I've been studying lately. I have nothing on that yet to publish, but the code is work in progress. And then mostly because I thought it was fun to compare against things like Chapel, and after you've written 3 or 4 different languages, I started writing other languages in my free time, including all sorts of weird stuff that I don't understand and for HPC purposes would be total trash. But we now have Octave and Lua and some other things in the project if you care about that. And I'll show data at the end. So if you want to look at the project, some people get a little confused because maybe my idea of a directory organization is the wrong one. There's a whole lot of stuff in the C11, C++, and Fortran directories. Like maybe in the C++ folder, there's like probably 100 files, and you just look at the name and you can figure out what they're doing. I apologize if the organization is confusing. I'd be happy to take pull requests or commentary on that. But for me, the build system runs better if I don't have folders. So it's kind of me being lazy. So this is a study from 2016 but we focused on distributed memory. I'm going to start here because if you haven't read this paper, maybe it's good to have the pointer, but I want to show how we were able to expose some relatively interesting behavior in programming models with what we have. And that I think is a validation that, hey, you can actually learn things from simple codes. So this is sync P2p. So this is distributed memory, which means it's basically a baton passing benchmark. You do a small amount of compute, then you send a signal from processing element from I to I+1 saying, okay, the data that I have produced is now ready. So producer consumer relationship. And it proceeds to fill the whole machine as it starts pipelining. So you start out with only rank 1 is computing, or only rank 0, and then by the time you get down a little bit, you're now filling the machine. So not too surprising, since that pattern matches perfectly with MPI send receive. It does quite well. Although you can see here that we wrote MPI shmem, that means MPI with shared memory, using MPI win allocate shared from MPI 3. Turns out that doing load store or atomic synchronization is faster than send receive within a node. That is obvious enough, but it's nice to see it and measure it. And it's a non-trivial difference when you get into a strong scaling limit. So this is a strong scaling benchmark on a Cray X Edison, I believe. And all the details are in the paper. If you can't download it, I can send you the PDF. If it's because it's not open access, unfortunately. But you can see here quite a bit of differences just between MPI shared memory and flat MPI. Shmem does pretty well. We didn't profile every last thing to the instruction, So I can't root cause every single data point here, but you can see there's some pretty significant differences. Berkeley UPC with semaphores is not as good as Cray SHMEM. That's on a Cray machine. That's not at all surprising. Cray UPC is rather disappointing. I don't know why, but we wrote the same things, and the people who wrote this stuff in many cases actually spent a good deal of time working with either the creators of the model or had some experience of their own. And so we feel like these are representative results. The Grappa team, worked with us on this. We weren't qualified to do anything with Grappa. I think it's admirable that that they don't win, and yet they were willing to participate. I think it's easy for a lot of programming model creators to show off and publish results when they win, but being able to publish when you lose, I think, is also really important and shows that people are serious about being evaluated. So here's a different one. This is Transpose. This one is really, I like this one a lot because I'm kind of a network junkie at times. So not too surprising. The bandwidth, the bisection bandwidth is the bottleneck here, and it grows as you increase the size of the system until you get to 1,536 cores, which I can't remember the node count. I think that was 512 nodes. But I apologize. I didn't memorize the paper last night. But what you see is really interesting is that around 1,500 cores, almost all the models turn over and start going down again. And this is really easily understood in terms of packet size. So for the models that are communicating with one process per core, the message size here at the crossover point is 8 kilobytes, and then it goes down quadratically because that's how transpose decomposition works. So as the message size goes down rapidly from 8 kilobytes to 128 bytes, you see the performance going down. This is pretty obvious. Everybody knows that your bandwidth efficiency in any network is pretty good for a page size or 4K page or above. But you switch protocols, you switch packet efficiencies, all sorts of things change. But what we see here, of course, is that the models where we're doing MPI plus X don't have this behavior because obviously you only have 1 or 2 communicating ranks per node. So the results are what you'd expect. This is useful in terms of understanding the quantitative details of why you would switch to a hybrid model in some communication pattern like this. We see this exact behavior in NWChem, which does a tensor transpose in distributed memory. We've seen exactly this characteristic for years, where you want to basically use 1 or 2 ranks per node in the transposes because you saturate the network and the performance is sad as you're totally nuking the network with all traffic. So there's also this funny bump, by the way, if you're looking at the MPI RMA fence. I never root caused that because the behavior changed with shortly after we published the paper, or that I think it was like the night before I gave the talk. They did a driver update, and Cray MPI didn't do that anymore. So it's probably some very subtle packet size network protocol effect. And of course, I didn't have source code, so there's nothing I could do. So we concluded at the end of this study, I think in hindsight, everybody seems to have agreed with us, not too surprisingly, that MPI was going to stick around for exascale, that we were not going to throw all the code out and start over. So the question is, now what? If MPI is going to be our distributed model, or at least something that looks like MPI, PGAS or whatever, we're probably not going to write our MPI or our exascale MPI codes with C89 and OpenMP 3.0. And so we began a study to look at what the node programming model would look like. So the hypotheses I had, I think it was about 2016 when I started doing this. Modern C++ was going to be important. At the time, I was true to my Argonne education, a C++ hater. And so I went into this with a great deal of skepticism, but my friends at Livermore and Sandia were quite convinced that modern C++ was going to work. I now believe them, but that's because I had the data. Anybody who doesn't like modern C++, well, they're probably going to use OpenMP. There's a handful of other things. Some people do OpenCL and some other stuff, and sometimes people layer things with DSLs. But outside of modern C++, the standard model is going to be OpenMP 4 or 5, whatever it is. There's also quite a bit of adoption of either proprietary or non-portable programming models. And if you want to convince those people to stop doing that, you need data. And so, coming from the perspective of not the company that does CUDA, if you're building GPUs, you need a way to convince CUDA developers to do something else, and having data is really good. So we built the data for that. And below the top 10, not everybody's going to go for peak flops or peak anything. We've already seen some adoption of Python and Julia in serious HPC purposes. It's worth evaluating those. And then, as we've now seen, it's obvious in hindsight, but there was certainly an expectation that at exascale new things would emerge, and they would need to be evaluated. So it was a funny coincidence for me, because I actually started studying SYCL before it was relevant to my day job. I had found it in slides from Michael Wong when I was looking up information about Cocos and Raja, and I saw this thing called SYCL, and I said, oh, well, that's interesting. That's kind of like Cocos and Raja. We'll see how it works. And then a short while later, it became very relevant to my day job, and I think some folks know about that. So in terms of the model support, relevant to what I just said, for the languages described, we have a sequential implementation. We have OpenMP implementations. 3 check marks mean that we have the traditional CPU way, the task-based CPU way, and the GPU target way. We also have an MPI implementation in many cases. I haven't done a lot with MPI recently because I feel like MPI is pretty good and doesn't need that much study now. But I've started working on some new RMA versions that will be ready someday with MPI plus multi-GPU stuff. We have a PGAS model represented wherever possible. With Fortran, we use co-arrays. We also use global arrays, Grappa, UPC, SHMEM. And then, of course, Chapel is a PGAS model, and so it gets that. But there's a version that is designed to be distributed like PGAS and one that's not. We use C++ and C11 threads where they exist, although it's not a particularly interesting result. And then we have all this other stuff like Cocos and Raja, TBB, multiple versions of SYCL, OpenCL, CUDA, HIP, OpenACC, NumPy, even did a little bit with PETSI just for giggles. And then ISPC, which really isn't C, but and that one will probably move folders someday. But anyway, so there's a lot of stuff in there. And the reason this might be interesting to some of you is if you've ever wanted to do an all-to-all comparison without learning all the other models, if you can fit what you want to do within the PRK framework, you can just implement whatever your new thing is or whatever the thing you're trying to study. And if you do it in a objective way relative to the other models, then you can just run 25 other programming models and get data. And so in this sense, it's kind of like NAS parallel benchmarks in that you can do these studies. So my C++ stuff is already out there. There's at least a couple of YouTube videos, and slides and a paper. So I'm not actually going to rehash a lot of that. I'll just summarize one of the, when we started looking at this, when we were working on, one API, we basically went out and said, well, what else is out there? What do they have, and what do we need? And so what you can see is that everybody has parallel 4. Not every model has a nested parallel 4, and this is for me as a matrix tensor type person is it's really annoying when I use a programming model and I can't write a 5-dimensional loop nest, for example. As somebody who does a lot of dot products and related mathematical operations, it's really annoying when I have to write a reduction by myself. Inclusive and exclusive scan also matter to people. And then, it really matters how you express memory management in a programming model.
because that impacts hardware support. So if you rely on, malloc and new, then you're requiring the hardware to do some stuff in a heterogeneous environment. Whereas if you've got opaque containers, life is better. So you see here, there's a pretty clear consensus that HPC users who would be using Raja or Cocos or OpenMP have some demands. And one of the things that we noticed very clearly when we were looking at SYCL 121, which is where things were until very recently, there were missing pieces. The memory management wasn't what users wanted. The reductions and other things were not there. And what you can actually see in this is the influence on SYCL 2020, which we, obviously this not like the PRKs were unique in this respect, but we were able to see even from the PRK ports what the differences were with respect to, say, TBB or Cocos and Raja. And make some changes. And then we're able to measure a lot of the impact of these things because we can show the difference before and after with which memory management techniques, etc. So here, these are going to be some performance experiments. Again, these are designed to say software versus software, or look at that funny curve. We learned something here, and not designed to be absolute measurements. So I already said that. And again, all of these are not optimized. Stream is pretty easy to get the right answer. The stencils are not anything you would claim to be super good, but we'll see they show off some interesting software artifacts. So Prk Stencil, this is from a while ago on KNL with C++. And this is, I think, a really interesting one from the perspective of productivity. So I wrote these things, and I wrote them all pretty naively. I wrote this, two-dimensional loops for stencils, and I run them, and TBB really won by a lot. And that was probably would have been music to the ears of all of my friends in the TBB team, but it didn't make sense. So you say, okay, why is TBB twice as fast as OpenMP in this environment? And it turns out it's because the TBB API for parallel loops actually forces you in just merely to write parallel loops. You have to create a, create tasks that correspond to cache blocks. And so merely by following a trivial TBB template, I wrote a cache blocked implementation and things were good. OpenMP, consistent with its prescriptive nature, did exactly what I told it to do and ran through all the data sequentially, which ensured that it hit the bandwidth limit rather quickly. And so obviously I learned from this, okay, I've got to write the same version in OpenMP that TBB was doing for me for free, which wasn't that hard. I just had to make them match up. And I learned, okay, TBB makes you do a little bit more work than TBB, not a big deal. Cocos and Raja have the similar ability to do the blocking for you, but you have to tell it. The other thing you can see here is that if you're going to do dynamic load balancing or task-based programming, TBB is a lot more mature than the OpenMP stuff. OpenMP task loop does not compete with TBB last time I checked. Hopefully that will improve. You can also see that the Parallel STL, while based on TBB, because it doesn't expose the same multi-dimensional loop blocking template that TBB does, isn't able to take advantage of that. Clearly, you can make it happen, but you have to do it yourself. And this, this is kind of a productivity measurement right here. So I fixed that. I wrote the exact same thing in OpenMP that I wrote in, or that was coming out of TBB, and we see the results obviously change. The reason you see the difference, TBB goes up past OpenMP, I think this is a unique aspect of the two cores per tile cache hierarchy and the way that OpenMP does scheduling versus TBB. It doesn't, it's not critical. They're close enough, and obviously blocking parameters and things make this is somewhat volatile measurement. So I'm calling it a tie because it, the noise is on par with the differences here. So is switching over to A64FX. This is really recent. I measured using the Georgia Tech machine. They were super nice and let me measure stuff because I thought it'd be fun. So this is PRK end stream. It's not at all interesting. It's the number you'd expect, give or take, 800 gigabytes a second from HBM2. The ramp is, ramps to about 16 cores. This is spread affinity, so you'll saturate faster than if you do close affinity. You see the compiler language stuff doesn't matter, other than Fortran wins by a teeny bit. Yay, Fortran. So here's the actual stream benchmark. And I want to emphasize here, this is not the peak result. This is just what I got with the Cray compiler with no special options. I've confirmed that the Cray compiler does not have the trick options that the Fujitsu one does, which are explained in the slide deck linked below. But this is the point I was making before about compiler and code generation. Is you can see here, we've got 800 gigabytes a second with, I think it was 02 or 03. And here, same flags, you lose 200 gigabytes a second because you're losing that magical store or whatever it is. And I think this means that you'd really want to use the one that's more stable and relative to compilers. Obviously, the Fujitsu folks and anybody who reads their documentation will know how to measure the bandwidth at the peak, which is 840. But unless you're willing to apply those compiler options in all of your bandwidth-bound application code, this might be meaningful to you, unless you're doing accumulate and then you don't care, and you can know that with the PRKs. This is a funny one. The PRK implementations in the C++, we have cache blocking implemented. In the C99 ones, we don't, because I haven't touched them in a while. And this is a big surprise that blocking is bad. Doesn't mean that some version of blocking isn't good. It's just our version of blocking that works everywhere else isn't good. I'm not an A64FX performance ninja by any stretch, so it is what it is. But this is very different. This is the opposite of Xeon. So Xeon blocking helps. Xeon has this gigantic L3 cache, and much prefers that you do cache blocking. Even the naive, simple version that we do in the PRK, and doing the untiled version hits the DRAM limit rather quickly, which is obviously lower than the HBM2 limit. So this is an example of something where you'd say, okay, if I'm going to really invest a lot of time in performance optimization of my stencil codes, I'll end up finding the right version anyways. But if you don't do that, then you want to at least know whether or not you should be tiling at all, and maybe figure out which type of tiling you would use on a different architecture. So this was a surprise. I'd love to understand this more. Whether or not I have time is unclear. This is Transpose. This one is interesting. I did not read the assembly yet, but you can see there's this beat pattern or stair step at multiples of 8. I have a feeling this is because the compilers treat nested multidimensional loops and arrays better in Fortran than in C++. I think everybody knows Cray Fortran is a very, very good Fortran compiler, and it's not surprising that it does a good job. It is possible either that I have written code in a inappropriate way for the Cray C++ compiler, or perhaps it's just unable to do some of the loop transformations or interleaving or whatever it is, or it's an SV512 thing. I don't know. Again, this is something that I really like having these codes to run as a smoke test on a new machine before I go into all the details. So I already know from this that there are some interesting characteristics between languages and within blocking sizes that I would go study if I was going to do, say, some quantum chemistry kernel where transposes were really important. So Wavefront, there's a bunch of implementations that all have P2p in the name. This is the code sequentially. It's a loop carry dependency. It is very, very simple. You cannot update element ij until the trailing neighbors, top, bottom, and or top left and top left diagonal are fulfilled. So this is related to dynamic programming or ParHMM, which of course is doing string matching with dynamic programming. It also came out of NAS-LU somehow. And it's also a gross simplification of
the deterministic neutron transport codes in places like NNSA and CEA, where they do Kripke and Snap, for example, do this with different decompositions, but ultimately they have this loop carry dependency. So it's a really good way to torture the hardware, given that you can't vectorize this because, or at least you can't vectorize it using any traditional method, because there's no data parallelism. It is at least not in any contiguous dimension. So we did a whole bunch of work on this. So you can read about this. None of these are original ideas in terms of how to optimize them. There's Vivek Sarkar has a great paper on changing the iteration space and doing OpenMP do across here, which I learned a lot from. So what you can do here is, of course, if you go across the anti-diagonals of the matrix, it's like taking a deck of cards and tilting them over. You now have parallelism along all these columns. But they're not contiguous, and so therefore you get the parallelism, but you make your memory access terrible in the process. So we studied this one anyways, just for completeness. So if you have an architecture like a big CPU that can run through sequential code quickly, this is very, very bad. On the other hand, if you have something like a GPU, where the sequential thread performance is absolutely terrible and you must have parallelism to accomplish anything, this is good because no matter how bad the access patterns are on a GPU, if you can pump a few thousand threads, you can hide enough latency and it sort of works. So this implementation is not great, but it is better than a sequential one on some architectures. So you can see here, it's clearly terrible code. You're doing inner loop parallelism. Every single one of these SIMD operations, if they're generated, is a gather, and that's obviously bad for performance. So we can fix this by amortizing synchronization in two ways. The first one is we can take those anti-diagonal sweeps, and we can not do a barrier between everyone, but we can actually, sort of unroll that and do a bit, do a stripe. This is in the literature, people talk about hyperplanes. And there has been some work in the past on hyperplane algorithms for this on GPUs. I think both for bioinformatics and neutron transport workloads. You can also do something that's, if you're a physicist in, renormalization group, you can create you coarsen the lattice by grouping a number of these points together and then treating them as sort of a supercell, and doing task-based synchronization between those supercells. And both of these are effective, but whether or not they're good depends on the architecture and the runtime. And so we'll show this. You can do a lot of pencil and paper analysis on where based on the cost of a barrier versus a task synchronization where they should land, or you can just measure it. So the task-based implementation, I happen to really like this from the perspective of this is code that actually makes me happy to write this thing. And I'm going to go a little bit faster because I'm coming on the end. Do across looks about the same. Turns out compilers do a bad job with this today, or at least they did last time I looked. And hyperplanes, you have to do some arithmetic. I found the arithmetic hard. I wouldn't want to do it in 3D, but here it is. You can see on Skylake that hyperplanes do really well. The task-based implementation also does pretty darn good relative to the hyperplane one, given that the task-based implementation is something that you write and it makes perfect sense, whereas the hyperplane one, especially in a more complicated code, doing all the bookkeeping might be difficult, and I don't think any polyhedral compiler in production can do that today. The green line is the Rob van der Wingart highly optimized atomic implementation, which of course is quite good, but also really, really hard to write. And in our cases, I think it might be critically dependent on the x86 memory model, but we'll have to look at that again later. You can see here the do across version is terrible because compilers did a bad job. That actually has been fixed in the compiler that was used here. KNL, it's a similar story. The difference here is interesting. It has to do with how the task-based parallelism is done with Tbb and Openmp. So Tbb uses distributed task pools, Openmp uses a centralized one. And as you know, if you're on a Xeon with a shared L3, bouncing between L3 slices is a lot better than bouncing L2 to L2. on the distributed cache in KNL. And so that's the effect you see here, where the TBB runtime implementation does a really good job, and the shared queue, there's too many cache-to-cache transactions. I'm going to skip over this. This is not the most interesting GPU stuff. We did OpenMP target and host. It's the same memory system. You can see differences. GPUs don't like tiling as much as CPU does. That's obvious. Okay. Now, I'm just going to say real quick, what if we evaluate non-HPC models? Why not? I've already gone through the pain of writing Fortran and C++ and all this other stuff, and other people wrote Chapel. So why not write a whole bunch of other crazy stuff and see what happens? So I have no expertise in any of these languages. I was at one point in my life marginal at MATLAB. So I had to learn all these, and clearly I haven't made a lot of progress. And if you look at these, fortunately, somebody who actually understands Rust helped me out with that one. Please, by all means, look at the code. I'd love external contributions here. So if we've written some of these things with Python, we wrote super naive Python that runs through the interpreter, Numpy, which actually is pretty good, and then MPI for Pi with help from Lissandro, who actually knows what he's doing there. So we wrote a lot of these, and then we can measure them and get some interesting results. So I just ran this on a Hades Canyon Nook on my desktop. There was a browser open. This is not super scientific data. So look at, put 10% error bars on everything. So the left column is something that fit in L3. The reason I did that is you can imagine how when you're running at 4 megabytes a second, it takes a really long time to do some octave measurements. So obviously I killed off the super slow models when I did a measurement that actually used more memory than fit in cache. You can see here, a lot, the peak is clearly around, 30 gigabytes a second for this memory. All the compiled models with GCC do about the same, no surprise there. C11, I don't know why C11 is 10% better. I think that's probably, some weird thing that happened on the system. May have been noise, who knows? I need to read more assembly. For each in the C++ STL takes a little bit of a step down, presumably compiler quality there. Rust and Go disappointed me, considering they're supposed to be the next generation C that's amazing for systems. Clearly it's user error because they're not perfect. Java does surprisingly well. That one freaked me out. I actually ran it through vTune and measured the hardware counters because I did not believe that Java could be reasonable. I have now relented, and Java is apparently reasonable for what we're doing. So good on them. Julia is also really cool. Julia does really well. That's not surprising to people who like Julia. But if you are wondering about Julia, at least for our studies, if you use it properly, and invoke the JIT compiler, it can do some really nice things. And the code doesn't look so bad if you're comfortable with MATLAB Fortran syntax. NumPy didn't do as well as I'd hoped. I think some of this will depend a little bit on the details and the implementation. I think there may have been, I may have used the wrong distribution here. Who knows? But NumPy is usually a lot better than, or is certainly a lot better than regular Python. We also looked at Transpose. This one, of course, is measuring something besides just the interpreter overhead or whatever it is. Java does remarkably well. Who knows why? I need to read more assembly or something to figure that out. I think it may be that the JRE is actually turning on turbo or something prior to the thing running. I need to go study that more. But you can see here, you can see some differences. In Fortran, if you use loops, you can write the most compact version of Transpose. If you use intrinsics, you actually have to run through the data twice because of how what we're measuring, and that costs you a little bit of the bandwidth. I'll skip this. This just shows that MPI for Pi is awesome, especially if you're measuring something other than vector addition. So we saw a bunch of interesting stuff here. It's kind of interesting to compare languages like this. There's a lot of other ways to compare languages, but actually compared to some of the stuff I've seen with the computer languages benchmarking game, CLBG, whatever it is, and some other papers that, where they compared power analysis and language that I think is terrible. I think it's actually better than those. So, I'm totally biased and maybe it's not anywhere near the best, but at least I think it's a pretty objective study of ways to compare languages doing simple things and determine which languages might have a hope of processing data at DRAM speed and others which will process it at the speed of some interpreter. So we've evaluated a lot of things. We've evaluated C++ models like SYCL versus Cocos. We've evaluated languages, whether it's Fortran versus Julia. We've done things with GCC versus LLVM versus other compilers. We've evaluated runtimes and distributed runtimes and runtime semantics or programming model semantics as well. And all of this is, you want to know something quickly. This is not the best way to create the pinnacle of academic knowledge and create something really fantastic that takes years of work. It's a way of getting something that is thought-provoking in a couple of days, and then knowing where to go next, maybe learning something that will help you with subsequent studies. And then, of course, as I've said many times, please, for the love, tune the code if you're going to actually measure absolute performance. Do not use untuned code for benchmarking. So I also want to emphasize, I guess this is from the previous slides, is I definitely did not satisfy any of Torsten's rules for good performance analysis. So please go download the code and redo the data if you want to publish it and do it right. Read Torsten's paper, it's great. And I will say, coming from industry, we've used these in a variety of purposes that I can't talk about. We have found them to be useful in doing architectural analysis as well as software analysis in our proprietary studies, where it turns out it's really nice to have a software that you can do quick and dirty experiments. Running through chip simulators is hard, and the PRKs are way easier to run through hardware simulators that do 1,000 instructions a day or whatever they are, than many of the other things out there. I will also say we've got a lot of help from experts like Lisandro. We've also found that Yijan from Georgia Tech was able to contribute as an undergrad. He wrote me out of the blue and said he was looking for something to do over the summer, because COVID and all that. And he made a great contribution in a short period of time. So if you're a board academic researcher, regardless of how far you are along in school, if you know anything about any programming language, you can probably contribute to this. And then here's some citations just for posterity if anybody looks at this stuff later. So thank you. And I guess question time.
Thank you.
Thank you, Jeff. This was a fascinating talk. I'm impressed at how well Java was doing. It's very strange. So before we move to questions, I just want to mention that our next SPCL Bcast will be on the 25th of February. Please check our website. We'll have more details up on this soon.